Hello students, and welcome to our next video here on calculus. We've been looking at exponential functions, and now we're going to look at the inverse of those, how to undo an exponential. We do those with logarithms. Because we've been dealing with exponentials with a base of e, then we're going to look at logarithms with a base of e as well, which often we call natural logarithms. So let's have a look here, just a bit of a reminder about exponentials. You can generate not just exponentials, but inverse functions. You can generate inverse functions by swapping the x's with y's and vice versa. So, I could say that the inverse of y equals e to the x is x equals e to the y. However, to make y the subject of that again, I would need to take the log base e of both sides. Okay, that's how we undo that exponential. So the inverse of y equals e to the x is y equals the log base e of x. Now, this is a particularly important function, and we're going to refer to it with this definite pronoun the, so it's going to be the logarithmic function rather than just a logarithmic function. Anyway, and we use that abbreviation ln, right? We don't necessarily have to write log base e, right? We can just write ln is understood as the log base e. We're asked to graph that from 0 to 4. So I'm just going to draw up a little table of values. We can use our calculator, right? So here's my calculator. And now if I want to find the log of 0.5, I can use this ln button. Oops, I have to move that a bit more, don't I? 0.5 equals, okay, let's say 0.7, negative 0.7, because I'm not going to graph it more accurately than that. The log of 1, well, we should know this one. What's the log of 1? E to the power of what equals 1? E to the power of 0 equals 1. Okay, the log of 1 is 0. The log of 2, well, it's got to be just less than 1, doesn't it? Because E is about 2.7, so 2.7 to the power of 1, or 2.7 to the power of 1, would be equal to 2.7. So to raise 2.7 to the power of something and get 2, it must be a little bit less than 1. Right, let's just confirm that. The log of 2 is equal to 0.7-ish. The log of 3 should be just more than 1. The log of 3. Here we go. And the log of 4. Hopefully you've been writing those down. Let's move this way. And here they are, right? I've rounded them off. They're all fairly approximate, but to be graphing them on here, they're going to be fairly approximate anyway. So I've got a set of axes. I'll chuck some labels on there, my x and y, at least the x. They're neatly spread out. Now I know I need to go as far as 4, and I need to go up as far as 1.4, and a bit of negative down here. So now we'll just plot those points on there, and you can see we get this sort of a thing. If I'd been a bit more proactive and had drawn the graph of y equals e to the x on here, we'd see that what we've got is a reflection in the line y equals x. Okay, that's what happens with inverse graphs. So now I run a nice smooth curve through there, and what I find is I have a vertical asymptote that is the y-axis. And it continues to increase off to the right, albeit slowly. Now, because my domain was strictly greater than 0, and I've got an asymptote here, I can just have an arrow, because that's going to continue to get really close to without equaling 0. But it's got to be strictly less than 4, so I don't want it where it's equal to 4, so I've put an open circle there. If I was just drawing the graph of log of x, then I'd have an arrow continuing off here, and it would continue to increase, but reasonably slowly. Okay, that's the first example there, graph of log of x. Now, we're going to solve a couple of exponential and log equations. If you remember that the inverse of a log is an exponential, and the inverse of an exponential is a log, these are reasonably easy to solve. So if e to the x equals 10, look, I'm just going to guess here that x should be something like 2.7, well, 3 squared is 9, so it's going to be about 2. Right? It's going to have to be a little bit more than 2. 2 cubed is 8, Yeah, so it's going to be somewhere between 2 and 3, I suppose. What I do is I take a log of both sides, a log base e of both sides. And that gives me the log base e of e to the x, which just means x. Right? The log base e of e to the x is equal to x. That's another way to write that expression. And then I get the log of 10. So x is the log of 10, and if I pull out the calculator, the log of 10 is equal to, there you go, 2.3, as predicted. So about 2.30 for 2 decimal places. Now over here, I've got a log equation, and I need to solve that. So I'm going to make each side the exponent, the power. So I'm going to have e to the power of the left-hand side and e to the power of the right-hand side. And what happens there is the sort of e and the logs cancel out. So I get 2x plus 1 equals e cubed. It's one of our sort of basic log laws. Now if 2x plus 1 equals e cubed, remembering that e is, while it might be irrational, it is constant. We just make x the subject of that, and that means that x is e cubed over 2 minus a half. Let's grab the calculator. So e to the power of 3, and we can use our fraction. Oops, not like that, is it? I can't even find the delete button. Okay, let's put our fraction here. E to the power of 3 over 2 minus, I'm going to save myself on the fractions here, 0.5. Okay, e cubed over 2 minus a half, about 9.5. Oh, 9.54, sorry, 2 decimal places were asked for. So there we go. Solving exponential and log equations. It's fairly important. There's nothing very new there. We're just using a base of e. Previously, we've done them with all sorts of different numerical bases. So that's it for this exercise. Just a reminder, the inverse function of e to the x is the log base e of x, or ln of x. The domain of that function, of log of x is always greater than 0. Okay, x is greater than 0 is the domain, and the range is all real y. E to the log of x equals x, and the log of e to the x equals x. Okay, that's it. If you've got any questions, make sure that you write them down so you don't forget. Ask me in class. Other than that, our next exercise is exponential rates. Okay, a bit of rates of change, and I'll see you then. Thanks, guys.